Electrochemistry. Leo goes Gur. You may have seen this before. This is an acronym. If you can remember this acronym, it's going to help you a lot to remember a lot of the things in the unit on electrochemistry. In electrochemistry, we are dealing with what we call oxidation reduction reactions. We also shorten that to redox reactions. Reactions can be classified by three ways, and one of those is classifying reactions as acid-base. Another is precipitation, and another is redox. So one way to categorize all reactions is to put them into one of those three categories. First, what is redox? It's an acronym. It stands for lose electrons, oxidize. So whenever a substance loses electrons, it is oxidized. And what is the other part? Goes Gur. So Gur is gain electrons reduced. So whatever gain the electrons is reduced. When we look at this, we can say oxidation is an increase in oxidation number. Those things have lost negative electrons, and so they become more positive, so their oxidation number increases. Reduction is when something gains electrons. Gur, gain electrons reduced. And if you're gaining a negative electron, the number gets smaller. So it's a decrease in oxidation state. One thing we're going to use a whole lot is a reduction table. A reduction table tells us the likelihood of a substance to be oxidized or reduced. And it puts it on a value with a voltage, and that comes in handy because the voltage will tell us whether or not a reaction occurs. And if it occurs without outside intervention, we say it's spontaneous. So there's some things I want you to notice here on the table. First of all, it's a reduction table. Every single substance on here, we see electrons on the left-hand side. So that means the electrons are reactants. That means they are gaining electrons, so it's a reduce. So we say it's a reduction table. And the other thing is everything on here is a half reaction. When oxidation reduction reaction occurs, one half of that is a reduction, the other half is an oxidation. So if we wrote every single one of these values in reverse, the reactions, and if we change the sign, multiply every sign by negative on the voltages, we'd have what we call an oxidation table. But we look at it just from the perspective of a reduction table, and so we're just going to look at a reduction table and not ever an oxidation table. What we're going to also do is combine these and hopefully get a positive voltage when we see whether or not a reaction occurs or doesn't occur. If it occurs, it'll be a positive voltage. Here's an example. Select which of the two reactions occurs spontaneously. Remember, spontaneous means it's going to have a positive voltage. Write the half reaction for the reduction and the half reaction for the oxidation. The reaction could either be putting a piece of solid nickel in a silver solution or putting a piece of silver in a nickel solution. Now, what would that look like in the lab? If you looked in the lab, the first reaction would look like this. A silver solution we've used quite a bit. Now, often you may see silver is stored in a brown bottle because it reacts. Silver is often stored in a brown bottle because it reacts with light. And a silver solution looks just like any other solution. There's no color at all to a silver solution, so it would look just like water. And so a nickel would be a solid metal. So that would be putting nickel into the silver solution. The other reaction would be a nickel solution. And nickel solution is actually a nickel compound has a light green color. And when you dissolve it in water, you get a green solution. And you'd put a piece of silver in that nickel solution. Now, one of these two reactions occurs. The other does not. The one that occurs, we say, is spontaneous. It would have a positive voltage. The other one does not. So how do you determine that? Well, we can actually put the substance in there and watch it. Another thing we can do to verify that or to go along with that is to look at the values on the reduction table. So let's do that. So in the reduction table, here what I did is I highlighted the only two substances we're concerned about. That is the silver and the nickel. When you do this, and I wrote this at the top because that's extremely important, the most positive half reaction occurs as a reduction. The most positive half reaction occurs as a reduction. So we have two substances we're looking at here. We have silver. Now notice I have both forms of the silver. I have a solid silver and silver ion. Then I also have nickel solution, which is nickel 2+, and solid nickel. Now the way to remember to do this is the most positive half reaction always occurs as a reduction. So if I look at these two values, I have a positive 0.8 and a negative 0.28. So that means this silver is going to be reduced. That means a silver solution will react with a nickel solid, because what happens, the first reaction will be written exactly as is, but the second reaction will be reversed, and that will be our oxidation. So you want to reverse the second reaction. The other thing you can do is go ahead and add up the voltages. If you reverse this and you add up the voltages, you see the voltage value would be 1.08 volts. And I actually looked on another table and it had 0.25 for the nickel value. So later on you'll see that I use 0.25 instead of 0.28. This would be a positive value. In summary, the most positive value is written as is, so that's our reduction. The most negative value, the less positive value, is written in reverse, and that's our oxidation. So the silver solid is a reactant, the nickel ion, nickel 2 plus and 2 electrons are products, and then we write for the voltage a positive 0.28. So let's see how that looks. Select which of the two reactions occurs. We said the nickel reacts with the nickel solid reacts with the nickel ion, and that occurs spontaneously because we got a positive voltage. But the nickel ion did not react with silver, so if we put solid silver in a nickel solution, there would be no reaction, and the voltages should affirm that. So how do you do? So first of all, we want to be able to write the reduction half reaction, the oxidation half reaction, the overall balance reaction, and determine the voltage. First of all, we know that this is a reaction that occurred spontaneously. So let's write the half reactions that go with that. So first, the silver reaction. We write the silver reaction exactly as we see it. So on the table we look, we see silver ion plus electron gives us silver solid. And the voltage that we wrote down for that is 0.80 volts. Now the second, so that is our reduction, because electrons are gained. Remember GER, gain electrons reduced. This is our reduction. Now let's look at the other half reaction, which is the oxidation. We write this in reverse. So we see the nickel solid goes to nickel ion, which is nickel 2 plus, and 2 electrons. Now, one thing you notice difference is there's a table that I have that has a 0.25, and so I'm using that voltage here instead of the 0.28. The only issue we have when we combine these, the number of electrons that are gained has to be equal to the number of electrons that are lost. So we see silver only gained 1 electron, whereas nickel lost 2. So what we need to do is increase an amount of silver to provide more electrons. So that means we're going to multiply this half reaction by 2. So we'll have 2 silver ions plus 2 electrons gives us 2 silver solid. Now we will not multiply the voltage by 2, because voltage is like density. It's an intensive property. A volt is actually a joule per coulomb. And so if we have a greater number of silver ions, we really still have the same number of joules per coulomb. When we multiply the silver half reaction, the silver half reduction reaction by 2, it looks like this. So now we have 2 silver ions plus 2 electrons gives us 2 silver solids. And so now we can sum these two half reactions. To do this, what we want to do each time is be able to cancel out those electrons. Electrons can appear in your half reactions as either a reactant when we see reduction or a product when we see oxidation, but those electrons should never appear in your overall reaction, because the number of electrons that are lost has to equal the number of electrons that are gained. So we simply sum the two reactions and the voltages, and we get this as our overall reaction. This is our overall net ionic reaction. And it's also a spontaneous process, because we see here we have a positive voltage that verifies that. A couple other things. So this is our nickel reaction. We say this is a nickel half reaction. Notice the electrons are products. Lose electrons, oxidize. So this is an oxidation. Look at the silver reaction. The silver half reaction, the electrons are reactants. If they are reactants, the electrons are gained. Gained electrons reduction. So this is our reduction. And then we combine those and we get the overall net ionic reaction, and also this is the voltage of the cell Notice it is spontaneous because we have a positive voltage. If we did the reverse reaction, if we did the wrong one, we would have had a negative 1.05, and that would have told us that would not have occurred because we had a negative value. A couple other things about this. Identify the substance that is reduced. So we look at the reduction. What is reduced is always going to be reactant, and so that the reduced substance would be the silver ion. Next, what is oxidized? That's going to be from the oxidation half reaction, and it's going to be a reactant. That's going to be a metal. So metals are oxidized, and so the metal that is oxidized here is nickel. Now we see metals can be reduced, but when metals are reduced, they are metal ions. When metals are oxidized, it's a metal that's a solid. I love chemistry. I love chemistry. I love chemistry.